So our goal in this video is to further our understanding of the conservation of energy and also to incorporate the types of calculations that we've been learning how to do in class. This picture should look familiar. It's from the lab that we did earlier in this unit. Let's just kind of remember how things went. We were asked to figure out what types of pie charts would apply here, and blue represented potential energy and green was kinetic. So at the very top, the skater had all gravitational potential energy and she wasn't moving at that point, so she had no kinetic. At a later point, there was some kinetic and some potential, but the size of the pie remained the same. This means that the amount of energy didn't change. It just divided up a little bit differently between the different forms. At the bottom, she was going as fast as she could, and all of her energy was in the form of kinetic energy. As she rose again, some of that potential energy switched back, some of that kinetic energy switched back into potential energy. You can see the blue growing. And then at the top, she stopped for a split second and all of the energy was gravitational potential energy. So again, at the top, all potential. Anywhere along in the middle, anywhere along the track, it has both types, or she had both types of energy. And at the bottom, all kinetic energy. We talked about how then total energy would be the kinetic and the potential all together. This was sort of what we were hoping to get out of that lab, that we saw the total amount always stay the same, but it just split up differently between the forms. So at the top, if we were going to think about the total energy, we might include that there's zero kinetic energy and it's all potential. Anywhere along the middle, we do have some energy of each type. And then at the bottom, there's no potential energy, none of the blue, all green, all kinetic energy. Now, if we look at this in terms of some numbers instead, the same sort of pattern should hold true. So, got some numbers here, just kind of made up for the amount of potential energy at the start, and then we'll assume that somewhere along the way, the girl has 100 joules of kinetic energy. And we're going to try to figure out what the unknown amounts are for those white boxes. And the key thing is that the total amount of energy is going to stay the same. And so if we can figure out what that total is at any point, then we know the total everywhere. So right at the beginning, we can say that the total energy is 500 joules. It's all potential, zero kinetic, but it doesn't really matter how it's split up. We just want to figure out what the total amount is. Then at the very bottom, when there's zero potential energy, all of those 500 joules must have switched to kinetic energy. So the total is staying the same. And again, anywhere in between, you're going to have some kinetic and some gravitational potential energy. But the total is going to have to be 500 joules. And so 500 minus 100 would give us 400 joules of potential energy at this point. This is really the big idea. When we say conservation of energy, we mean that the total energy at one location is going to be the same amount of total at another location. It might be different amounts of kinetic and potential, but the total amount, the addition of those two amounts is going to have to equal the same bigger value. So a strategy we'll use when we start putting some calculations into our work is we will figure out the total total energy, mechanical energy at some location, and then we'll use that total at a different location to figure out something we'd like to know, like the height of the object or the speed of the object. So let's take a look at an example here. A 3-kilogram ball is kicked upwards from the ground. The initial speed as it leaves the ground is 18 meters per second. And we can predict how high the ball will go using the ideas of conservation of energy. We'll start by determining the kinetic energy at the bottom. That's because the ball only has kinetic energy at the very lowest point. When it's at the ground, there's no potential, it's all kinetic. So the kinetic energy would be 1/2 times the mass times the speed squared. So 1/2 could be written as 0.5. We'll put in our 3 for the mass, and our 18, that's the number that has to be squared. We would grab a calculator and work through our algebra, and this comes out to be 486 joules. But again, this is a very important number. Because the potential energy is 0 on the ground where the ball starts, this is also the total mechanical energy. And that means that at any other point in the ball's motion, it has a total amount of 486 joules. So at the very top, the ball will actually stop for a moment and then start falling back down again. And if it stops, then its speed is 0, and then its kinetic energy is 0. So again, super important number now. Since the total energy is kinetic plus potential, if the kinetic energy is 0, then all of this energy is gravitational potential energy. And so now we can pull out a formula and we can figure out how high the ball goes, what the H is in our potential energy formula. Most of the numbers seem to be given to us here. Remember that little g is equal to 10 because that's the strength of gravity on the Earth. So we can fill in some of the things we know. We're going to have to do a little algebra to figure out what that H is. Let's talk through those steps. A good first step is to multiply the 3 times the 10 and get those numbers together down to one value. And then to get the H by itself, we would divide both sides by 30. So 486 divided by 30, definitely need a calculator here, comes out to be about 16 meters. So that's how high the ball will go if we kick it at 18 meters per second from the ground. We've now been able to make a prediction about what an object's motion would be based on some initial values. When you can do that, when you have a pattern that seems to happen over and over and over again, this ends up being something called a law. So when there's observations and we notice that a certain thing always happens, that's going to become a law in science. And this one is called the law of conservation of energy. That the amount of energy that you start with will equal the amount of energy later on. The energy can change from one form to another, but the total amount will never change. Another way that sometimes you hear this stated is that energy cannot be created or destroyed. However much you have to start with, that's how much you have at the end. In our example, again, we started with kinetic energy. All along, as the ball was traveling upwards, there was both kinetic and gravitational potential energy. It changed form, but the total amount would stay the same. And at the very peak, the ball has a 0 speed for a split second, and at that moment, all of the energy is in the form of potential energy. And again, that's how we predicted how high it would go. Sometimes people like to think about energy like money. That might seem strange to you, but money also flows between different forms. You can have money as cash, as coins. You can have money in a bank account. Or maybe if you're really with it, you might have Bitcoin. Okay, but you can store money in many different forms. But it just changes from one form to another. You can always track it. The total is always going to be the same whether if you have a $20 bill and you change that into a $10 bill and $10 in quarters, it is still $20. It's just in different forms. Similarly, there's a flow of energy. Energy changes from one form to another, just like money changes hands and changes from one form to another. But it never truly goes away. Energy should always be able to be accounted for as it moves from one form to another. Here's an example. Our energy in this area, some of it comes from coal originally. There's energy stored chemically in coal, and that is released, and it is changed into a form of energy related to electricity. That electricity is then powering your Chromebook, but your Chromebook is going to heat up, and there's going to be energy that goes into that form. So one of the things we'll talk about in the next couple of weeks is energy that goes beyond just the mechanical forms that we're talking about now, and we'll start seeing other forms of energy. Also, sometimes people say, wait a second, what do you mean energy never goes away? Well, it just turns into a form that we can't easily get back, and that's usually due to something like friction or air resistance. Any type of machine or activity, you're going to lose some energy to a form that is not easily converted back again, like heat. But a lot of times people are trying to get a process to be as efficient as possible, meaning that most of the energy comes back in a usable form at the end. For instance, there's been a lot of engineering into light bulbs because our old-fashioned light bulbs were less efficient. Our newer ones are more efficient. They don't put as much energy into heat. It's mostly light. And so we're getting more out of them. We see this with mechanical energy too. Like for instance, if you think about sliding down a slide at a park, you're going to maybe feel yourself warm up, as you slide along there. Roller coasters, of course, they don't go on forever. They eventually would slow down as things go. There really is energy that goes into a form that we can't get back. We have to refill. We have to put gas in cars. We have to feed ourselves with food. Okay, but these sorts of real problems where you start following how energy goes into a form like heat that you can't get back, those are pretty messy to deal with. And so when we first start off with physics, we assume that this amount of energy lost is very small. And so we do make the assumption that energy is completely conserved. Everything is perfectly efficient. The total amount at the beginning equals the total at the end. Let's look at one more problem as we close. So imagine dropping an egg off the top of the school, which is about 16 meters above the ground. Let's say that we notice or we measure that halfway to the ground, the egg is moving at 12 meters per second. We can figure out how much total energy the egg has at this time. We'll first look at kinetic energy. So that's 1/2 m times our speed squared. There's a 1/2 in here from the formula, which we can replace with 0.5. And there's a 0.5 for the mass. And then our speed is 12. Got to make sure we square that value of speed, and we end up getting 36 joules. The other part of energy is going to be the potential energy. So we would want to use mgh for this. Now, there is an h given, 16 meters, but that's not actually how far where the egg is at this moment. It has fallen halfway to the ground. And so it is halfway above the ground. We would want to take that 16 meters and divide it by 2. That is a divide, not a plus, kind of hard to see on the screen here. 16 divided by 2 would give us 8 meters. And so that's the number we're going to use in our calculation. Our mass, we're going to use 10 for little g like we always do with this formula, times 8. And this tells us that the egg would have 40 joules of energy due to its height above the Earth. So the total energy, which is the kinetic plus the gravitational potential, would be 76 joules. And then we can predict, using those 76 joules, how fast the egg is going when it smashes into the ground. It's going to be going faster than 12 meters per second because it's going to continue to speed up from that point. This 76 joules will all be kinetic energy when the egg gets to the bottom. It'll all have been changed into that form. And so we can start with the kinetic energy formula and fill in some of the things we know. We know our energy value. We know the 1/2, because there's a 1/2 in the formula. That's the first 0.5. And then there's a second 0.5. That's the mass of the egg. And our unknown is V. Now the V is squared in this formula, so we're going to have to do a little bit of algebra here. Let's first clean things up a little bit by finding out that 0.5 times 0.5 is 0.25. And then we would divide both sides by that 0.25 so that we get the V squared all by itself. And then lastly, we would square root both sides of the equation to find our speed to be 17.4 meters per second. That egg is going to be smashed.